The universe is designed for chaos, not code. Stars explode. Galaxies collide. The fundamental laws of physics push everything towards disorder, towards a final, bland equilibrium. So how did a dead rock, bombarded by radiation, floating in a hostile cosmos, suddenly learn how to think? How did atoms, with no plan and no purpose, accidentally write the source code for you? Forget what you've been told about a lightning strike in a warm little pond. The real story is crazier, messier, and it starts with the single most important event in Earth's history, the planet's first memory. And tonight, we're going to audit that memory against the unforgiving laws of physics to find out what actually works. Let's rewind the clock. Way back. 4 billion years. Picture the scene. The sky isn't blue, it's a hazy, toxic orange, with no ozone layer to block the sun's brutal ultraviolet radiation. The oceans are not calm expanses, they are global cauldrons of boiling, acidic water, steaming under the faint young sun. Volcanoes punch through the crust, spewing sulfur and hissing gas. And raining from the sky isn't just water, it's a constant bombardment of meteorites, asteroids, and comets, delivering a cocktail of exotic chemicals from outer space. This isn't a cradle. This is hell on Earth. But this chaos holds a secret weapon, gradients. That's a fancy word for a simple idea, a slope. A place where things can roll downhill. You know this intuitively. A hot cup of coffee cools down because the heat rolls downhill into the colder room. A dam generates power because water wants to roll downhill. Early Earth was a planet of 1,000 different slopes. There were heat gradients between volcanic vents and the cold deep sea. There were chemical gradients between acidic oceans and alkaline pockets. There were light gradients between the sun-scorched surface and the dark abyss. The entire planet was a massive, untapped battery, humming with potential energy, just waiting for something to plug into it. And life, it turns out, is the ultimate energy surfer. It doesn't just exist in the gradient. It is the gradient. So the power source is there. But what about the parts? The nuts and bolts. To build any machine, you need a parts list. For life, that starts with amino acids. In 1952, two scientists, Stanley Miller and Harold Urey, tried to answer this. They built a Frankenstein-style contraption of glass globes and tubes, filled it with a witch's brew of gases they thought matched Earth's early air, methane, ammonia, hydrogen, and then zapped it with artificial lightning. They were simulating primordial Earth in a bottle. After just 1 week, the clear water turned a murky, reddish-brown. When they analyzed that sludge, it was teeming with amino acids. The very building blocks of proteins, the molecules that make up your muscles, your hair, your enzymes, had just built themselves. No magic. No divine spark. Just raw materials and a jolt of energy. It was a scientific earthquake. It proved the parts weren't a miracle. The parts were inevitable. And they weren't just cooking at home. We find these same building blocks inside meteorites that have been traveling through the frozen vacuum of space for billions of years. The universe, it seems, is littering its sidewalks with the bricks to build a cathedral. Okay, so we have power, and we have bricks. But a pile of bricks on a construction site doesn't make a house. You need walls. You need to separate inside from outside. Enter the unsung hero of this story, lipids. Fat. Oily molecules. They have a superpower born from a simple phobia. They hate water. They're hydrophobic. Now, imagine tossing a drop of oil into a glass of water. What does it do? It forms a sphere. It's not a decision. It's physics. The oil molecules frantically arrange themselves to minimize contact with the water. Now scale that up. Imagine trillions of these simple fatty acid molecules, delivered by meteorites or cooked up near volcanic vents, floating in the early oceans. What do? They build rooms. They spontaneously curl into tiny, hollow spheres called vesicles. Little bubbles. Soap bag rooms that trap a sample of the outside ocean on the inside. Suddenly you have a protocell. Not alive. Not by a long shot. But it's an address. It's a container. It's a laboratory where the chemistry of life can get a private space to start working. A place to keep its treasures close. And once you have these rooms, they can grow by absorbing more lipids. They can get knocked around by waves and divide into smaller daughter rooms. We're not talking about reproduction. We're talking about simple, dumb physics. But it looks an awful lot like the beginning of a dynasty. So we have a power grid. We have bricks. We have rooms. But an empty room is just a box. What happens inside? That's where things get interesting. A reaction that might take 1,000,000 years to happen by chance in the vast ocean could happen in a second inside one of these tiny vesicles, simply because all the necessary ingredients are trapped in the same room together. But even that's not fast enough. Chemistry needs a kick. It needs a catalyst. A catalyst is like a professional matchmaker for molecules. It grabs the right chemicals, shoves them together in the perfect orientation, and makes them react thousands, even millions of times faster. So where did the first matchmakers come from? Forget complex proteins. Think mud. Common clay, like montmorillonite, has an amazing property. Its molecular structure is a stack of negatively charged layers. These layers attract positively charged molecules, like the building blocks of RNA, the simpler, grittier cousin of DNA. The clay acts like a chemical assembly line, grabbing the building blocks from the water and lining them up, click, 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 into long chains. No cell. No enzyme. Just wet-dry cycles on a muddy beach, turning a messy soup into the first lines of code. Geology as a writing desk. And that brings us to the biggest chicken-and-egg problem in all of science. The central debate. The heavyweight title fight for the origin of life. In one corner, you have Team Metabolism first. Their argument? Life didn't start with code, it started with a factory. Imagine a network of chemical reactions, a cycle, running on the surface of minerals deep within hydrothermal vents. A self-sustaining loop. Reaction A makes chemical B, which helps reaction C, which in turn helps reaction A again. It's like a campfire that learns how to gather its own wood. A self-feeding, self-perpetuating machine made of pure chemistry. Information, the code, would come much later, as an add-on to stabilize this already running engine. In the other corner, you have Team RNA first. Their argument? Forget the factory, you need the blueprint first. They argue that life began with a single molecule, probably RNA, that had the magical ability to make copies of itself. Information before metabolism. A recipe that produces more recipes. This single replicating molecule would make mistakes, mutations, and natural selection would kick in at a chemical level, favoring the molecules that were better and faster at copying themselves. The factory, the metabolism, would be built by this replicating code to serve its needs. So who's right? The factory or the blueprint? For decades, scientists hurled evidence at each other. But today, the answer is looking like both. And neither. They were asking the wrong question. It's not a chicken and egg problem if the chicken and the egg emerge at the exact same time. The best models we have today are hybrids. They suggest it all had to happen together. You need the rooms, the lipid vesicles, to keep the factory parts contained. You need the factory, the metabolic cycles, to provide the energy and building blocks. And you need the blueprint, the RNA-like templates, to remember how to build it all again. It's not a sequence. It's an arch. A three-sided arch that only stands because all three pieces, compartments, metabolism, and memory, are pressing against each other at the same time, supported by that constant flow of energy, that gradient we talked about at the start. How do we know we're on the right track? Because a ghost of this ancient past is still living inside every single one of your cells right now. I want you to think about how your body generates energy. It's not a fire. It's a hydroelectric dam. Every living thing on this planet, from the bacteria in your gut to the cells in your brain, uses the exact same system. It's called chemiosmosis. It works by pumping protons, positive charges, to one side of a membrane, creating a powerful gradient, just like water building up behind a dam. Then, it lets those protons rush back through a tiny, molecular turnstile, a protein called ADP synthase. And every time a proton goes through, it turns a little rotor, and that rotation smashes a phosphate onto a molecule, creating ADP, the universal energy currency of life. That's incredible. But here's the mind-blowing part. Those alkaline hydrothermal vents on the ocean floor? They are natural proton gradient batteries. The vent fluid is alkaline, rich in protons, while the ocean outside is acidic. The thin mineral walls of the vent are riddled with tiny pores, creating millions of natural compartments. Inside the pore, alkaline. Outside the pore, acidic. You get a natural, pre-made proton gradient for free, courtesy of geology. This isn't a theory. This is a fact of geochemistry. The slope was already there. Life just had to learn how to ski down it. And the fact that every life form still uses that exact same trick? That's not a coincidence. That's a smoking gun. It points right back to those dark, deep-sea vents as the most likely cradle for that first, tentative spark. Luca, the last universal common ancestor of all life, almost certainly lived off this free energy. You are the direct descendant of a rock that knew how to harness a battery. Alright, let's pause. Rehook. We have the stage set, the parts are available, the power is on, and we have a prime suspect for the location. So why haven't we made life in a lab yet? Because building the circle is hard. We've made huge progress. We've copied short strands of RNA without any enzymes, just using wet-dry cycles. We've grown vesicles, fed them fatty acids, watched them get bigger and divide. We've even built simple chemical networks inside them that amplify themselves. We've forged every single link in the chain. But we haven't closed the loop. We don't have a single, self-contained system that builds its own walls, powers its own factory, copies its own blueprint, and this is the crucial part, evolves. The circle is almost drawn, but the ends are still faint, refusing to meet. Now, this is where we have to slow down, at the very edge of what we know. Let's talk about that copying process. It's a razor's edge. Imagine you're copying a book by hand. If you make too many errors, the story dissolves into gibberish within a few generations. That's called the error catastrophe. Information is lost. But if your copying is absolutely perfect, 100% flawless, nothing ever changes. There's no room for improvement, no possibility for evolution. Nothing new is ever created. The sweet spot, the Goldilocks zone for life, is called the error threshold. It's where memory is stable enough to persist, but just sloppy enough to learn. To stumble upon new, better ways of doing things. Evolution isn't about perfection. It's about being good enough to survive and messy enough to improve. It's a musician practicing just a little out of tune, searching for a new harmony without losing the original song. And finding that balance, that perfect rate of error, might be one of the hardest tricks in the book. And here's another puzzle. Life is weirdly biased. It's one-handed. Many important molecules, including amino acids and sugars, are chiral. It means they exist in two forms that are perfect mirror images of each other, like your left and right hand. Chemically identical, but spatially opposite. Now, when you synthesize these in a lab, you always get a perfect 50-50 mix of left-handed and right-handed versions. But the life on this planet? It's a radical partisan. It uses almost exclusively left-handed amino acids and right-handed sugars. Why? How did it choose a side? Did it flip a cosmic coin that landed heads for 1 billion years straight? Probably not. The answer is likely a tiny bias that got amplified into a landslide. Maybe circularly polarized light from a nearby neutron star destroyed slightly more of the right-handed amino acids than the left. Maybe the surfaces of those chiral mineral clays preferred to bind with one hand over the other. The initial imbalance could have been 50.001% versus 49.999%. A whisper of a difference. But then, you add autocatalysis, reactions that make more of themselves. It's like a dance where a left-footed step is slightly easier to learn, so it teaches more dancers to use a left-footed step, until the entire dance floor is filled with only left-footers. That initial, tiny physical fluke gets locked in, amplified, and becomes a fundamental, planet-wide rule. And it's critical. Using only one type of hand allows proteins and DNA to fold into precise, stable, predictable shapes. Without this weird, one-sided obsession, complex life might be impossible. All of this points to a revolutionary idea. We've been thinking about selection wrong. We think of Darwinian selection, organisms competing. But the selection might start much, much earlier. As pure physics. It's a concept called dissipative adaptation. That sounds complicated, but the idea is beautiful. Under a constant flow of energy, systems that are better at absorbing that energy and dissipating it as heat will tend to persist and grow more complex. Think about it. A hurricane is a highly organized structure, a massive, spinning vortex. Why does it form? Because it's an incredibly efficient way for the warm ocean to dissipate its heat into the cold atmosphere. It's a structure born from a gradient. Before genes, before cells, before any kind of replication, selection favors patterns. It favors structures, whether they're whirlpools, chemical cycles, or protocells, that get better at surfing the energy wave. Life, in this view, isn't a miracle that happened despite the laws of physics. Life is what physics does given a rocky planet, a steady gradient, and a few billion years to practice. So, is life inevitable? If you have a wet, rocky planet with gradients, do you always get biology? Or did Earth just get insanely lucky, stumbling through a narrow corridor of 1 billion coincidences? This is the paradox that keeps astrobiologists up at night. The physics feels general. The chemistry feels contingent. Our job in this audit isn't to pick a side, it's to understand how the general laws of physics could have paved a specific, contingent path right here on Earth. How the universe's what if became our what is. Let's bring it all home. What is life, then? Maybe we can stop using a checklist. Does it move? Does it reproduce? Does it metabolize? Maybe a better definition is a process, not a thing. Life is matter that has learned how to use memory to get better at writing an energy gradient. It is a sustained conspiracy between pattern and flow. That ancient story is not over. It's written into your very being. Your body is a cathedral built from 4 billion-year-old tricks. Lipids from an ancient ocean are forming the walls of your cells. The ghost of a geothermal vent is running the proton water wheels inside your mitochondria, millions of them, spinning millions of times a minute, right now, as you listen to my voice. The first spark is still turning inside of you. And if it happened here, if rock, water, and sunlight can stumble into computation, into memory, why not elsewhere? Zoom out. On the ocean worlds in our own solar system, in the dark, geothermally heated bellies of moons like Europa and Enceladus. On the ragged, tidally locked edges of exoplanets trillions of miles away. Wherever gradients persist long enough, matter might be learning this same song, just in a different key. Not our biochemistry, but our logic, rooms, tools, and memory, powered by the flow. The cosmos could be humming with it. And that changes everything, doesn't it? If we do manage to close that loop in a lab, to coax a minimal living system into being, have we created life? Or have we just discovered a recipe the universe already knows by heart? This has profound ethical implications for our exploration of the cosmos. We need to be gentle, clever. Because on a world like Mars, or a moon like Titan, the chemistry might be on the cusp. We need to explore like cosmic archaeologists, not bulls in a china shop, because we might accidentally trample the most important discovery in human history just as it's getting started. And here's one final thought, a strange and wonderful crossroads. This entire process, of structures learning on a gradient, sounds eerily familiar. It's the exact same logic we use to train artificial intelligence. A neural network learns by descending a gradient in an abstract mathematical space, adjusting its connections to minimize error. A protocell learned by physically climbing a chemical gradient, structuring itself to better dissipate energy. The origin of life and the future of intelligence might be two verses of the same song. The song of gradient descent. We are listening to its echo, trying to learn its tune. So, the first memory wasn't a thought. It wasn't a picture. It was a simple, stubborn pattern in matter that survived because it was good at channeling energy. A dance between chaos and order. Rooms, tools, and blueprints, woven together on a loom powered by the Earth's restless heat. And we, with our thoughts, our art, our science, we are that pattern, 4 billion years later, finally waking up and trying to remember how we began. The first spark isn't just an ancient event, it's the engine that's still running inside of you. Now, that same process of learning is being mirrored in silicon. If life is what the universe does when energy meets memory, what happens when the memory we create turns back to reshape the very gradients that made us? We'll be auditing that question very, very soon. So think about this. If that ancient, physical memory is still turning inside of you, what is the most important lesson it has taught? And what will you do with it? If this audit blew your mind and you want to understand the next step in this story, how artificial intelligence might be following these exact same rules to create a new form of life, then I broke down the startling parallels in this video right here. It's waiting for you. And before you go, drop a comment. In this whole incredible puzzle, what do you think is the single biggest missing piece scientists still need to find? I read every single one. Subscribe, because tomorrow, we audit another piece of your reality. And you don't want to miss it.